Welcome to AI Podcast. Today we're digging into a fresh AAAI paper called Encoder of Thoughts. And the big idea is simple. If you show a language model the shape of a plan, not just the words about the plan, it gets better at planning.
Shape of a plan. I like that. Give me the one-line takeaway up front.
The authors, Yuxiang Zhang and Jitao Zhang, bolt on a small structural encoder that turns a plan's graph into an embedding the language model can read. No surgery on the model. Planning gets more reliable across a range of tasks and model backbones.
So this isn't about making the model bigger. It's about giving it better glasses.
Exactly. Think of it as handing the model a subway map of its reasoning instead of a paragraph describing the stations.
All right, set the stage. What problem are they trying to fix?
Modern language agents do multi-step reasoning with scaffolds like chain of thought, tree of thoughts, or react. Those are great, but they express structure as plain text. The model has to infer which step depends on which, just from tokens. That's fuzzy and gets worse as plans branch and backtrack.
So the gap is that structure is there, but it's hidden in a wall of words.
Right. And when you push depth or breadth, the context window fills up with verbose traces, making it harder for the model to keep the plan straight.
Enter Encoder of Thoughts. Walk me through what it actually does, step by step, but in plain English.
First, the agent builds a simple graph of its plan as it goes. Nodes are actions or intermediate states. Edges show dependencies, like this step must happen after that one. Second, a small graph neural network reads that graph and produces a compact vector that captures its structure. Third, they align that vector to the language model's input space, like adding a short prefix queue the model can immediately digest.
And you said no surgery on the language model, so we're not retraining the giant model, just training this sidecar encoder.
That's the idea. It's plug and play. You attach the encoder to different planners and different base models, and the interface stays the same.
Why should that help, though? The language model can read text. Why do we need a graph vector?
Picture giving directions. If I read you a long list of turns, you might get lost. If I show you a map, the layout makes dependencies obvious. The encoder is the map. It preserves topology, like which branches converge, and where a misstep would break the plan.
Nice. What did they test to make that case?
The paper evaluates on multi-step reasoning and plan generation tasks. Think problems where you must choose and order actions rather than just answer in one hop. They compare the same planners with and without the encoder, and they try multiple language models to check that the gains aren't tied to a single backbone.
Did they change prompting tricks too, or just add the encoder?
The core claim is that the large model's weights and the planner stay untouched. The only change is feeding in the structural embedding alongside the usual text.
Results in plain terms. Did it work?
Yes. They report consistent improvements in success rates for multi-step planning and reasoning. The pattern is that plans become more stable, with fewer derailments when the search space gets wide.
Consistent is good. Do they give a story for why the gains show up across models?
They argue the structural cue helps any model score partial plans more sensibly. When a plan has two branches, the model sees not just the words, but the branch layout, so it avoids tunnel vision.
Let's connect it to familiar methods. How would this sit next to Tree of Thoughts?
Tree of Thoughts explores many reasoning paths, but still represents structure as text. Encoder of Thoughts could summarize the current tree into a compact signal that guides which branches to expand or prune.
And with React, where the agent alternates thinking and acting.
Same story. The action history naturally forms a graph. Encoding that graph gives the agent a quick snapshot of where it stands and what depends on what, rather than rereading a long log.
I can hear some listeners asking about overhead. A new encoder means extra compute, right?
It does add a small model call. The open question is budget fairness. If your baseline used that extra compute for deeper search or more samples, would it catch up? That's the kind of equal budget comparison we'd want to see replicated.
Another practical question. Where does the graph come from? Are they handcrafting rules, or is it automatic?
The planner's own steps define the graph. But the sensitivity matters. If your edges are noisy or your states are mislabeled, the structural snapshot could mislead the model. Robustness to messy graphs is something to stress test.
Do they report ablations like swapping the graph encoder for something simpler?
They describe the components and emphasize alignment to the language model's space. But the summary leaves me wanting deeper ablations. For example, how much do we gain from the graph architecture versus just pooling tokens in a smarter way?
What about scope of tasks? Puzzles only or interactive environments too?
The headline categories are multi-step reasoning and plan generation. I'd love to see follow-ups on embodied tasks, like household simulations, or tool use in web environments, where the plan graph is naturally rich.
Reproducibility check. Do we have code links yet?
Not from the venue page summary. Independent replications and public benchmarks would make the picture clearer.
Let's talk about where the authors are from and where this appeared.
The work is by Yuxiang Zhang and Jitao from Beijing Jiaotong University, with an additional affiliation to Pengcheng Laboratory, and it's published at AAAI 2025.
All right, give me a concrete analogy before we wrap, something a project manager could repeat to their team.
Sure. Imagine your team's roadmap on a whiteboard. If you only keep a running meeting transcript, people forget which tasks block which. If you snap a photo of the roadmap and paste it at the top of every memo, decisions get better. Encoder of thoughts is that photo, except it's compressed into a vector the model understands.
That lands. And if someone wanted to extend this idea tomorrow, what would you try first?
I'd pair it directly with search. Use the structural embedding to prioritize which branches a tree-based planner explores next. I'd also pre-train the encoder on synthetic plan graphs so it starts with a sense of good and bad topologies, even before seeing a specific task.
Plus, stress tests. Deliberately corrupt the graph and see when the model gets overconfident. That's where safety considerations enter.
Totally. And finally, measure end-to-end cost. If you can keep the structural snapshot tiny and cached across steps, you might get both accuracy and speed.
Quick recap before we close. The paper says planning improves when language models get an explicit structural cue encoding the plan's graph. It's model agnostic, it plays nicely with existing planners, and it opens the door to smarter search.
And the caveats are compute budget fairness, graph construction robustness, and the need for broad reproducible benchmarks and code.
That's our takeaway. Give models a map, not just directions, and they plan better.
You've been listening to AI Podcast. I'm Ethan.
I'm Maya. Thanks for joining us, and we'll see you next time.